Well, here's a problem taken from an AP exam. This is from the year 1987. It's problem number 3 from the Electricity and Magnetism AP Level C exam. And it's a circuit that combines resistors with an inductor. This one might look familiar. We may have solved an example problem already in a previous lecture, a lot like this problem. But let's get into it and see what this one's all about. It shows us that the circuit has a switch S. Yeah, we see that. And initially, that switch is open, so all the currents at every point in the circuit is equal to 0. But then, immediately after the switch is closed, we have a few values we have to solve for. A, what's the potential difference across the 90 ohm resistor? What's the voltage from point A to point B? Well, immediately after the switch is closed, if currents are going to go from 0 up to any value, then the currents have to gradually rise to that value. They can't instantly do it. That's the behavior of inductance. And so initially, the slope of this graph is the greatest at time t equals 0. di dt is a maximum. And when di dt is a maximum, then the effective resistance of our inductor approaches infinity. So whatever amount of current is flowing through the battery and the 10 ohm resistor, it reaches junction A and has no choice but to continue on through the 90 ohm resistor. So all we need to do to answer part A is apply Ohm's law. Current is voltage divided by resistance, and immediately after, the initial condition for this circuit is that the inductor has infinite resistance, and so 20 volts is applied to a series combination that adds up to 100 ohms of resistance. So 20 divided by 100 is 2 divided by 10 is 1/5 of an amp. You might prefer to call that 200 milliamps. But that's not the question. It wasn't how much current is flowing through the 90 ohm resistor. It's what's the potential difference. So V equals IR. Now you might say, wait a minute. If you just use an equation I equals V over R, and now you're going to go back to V equals IR, that's like 2 steps forward and 2 steps back. But not really. This is a current of, 0.2 amps, 200 milliamps, multiplied by a resistance of, well, I'm not going to do the full circuit resistance of 100 ohms. Now we're not being asked for the voltage from point X to point B. We're being asked the potential difference from A to B. So when the 200 milliamps flows through just the 90 ohm resistor, then you get 18 volts. So this is effectively a voltage divider. You have 2 volts out of the 20 volts lost across the 10 ohms, and the remaining 18 volts is lost across the 90 ohm. Okay, what's the rate of change of current in the inductor? What is the initial slope of this graph? Well, if the voltage across the 90 ohm resistor is 18 volts, then the voltage across the 0.5 Henry inductor also has to be 18 volts because the two of them are connected in parallel. So this voltage is not only the voltage for the 90 ohm resistor, but the voltage for the inductor also must be 18 volts. But I know voltage for an inductor, at least in magnitude, is equal to the inductance multiplied by the rate of change of current. So the rate of change of current is equal to the potential difference, we'll call it VAB, divided by the inductance. This is 18 volts divided by 0.5 Henry. So we get a value of 36 amps per second. Great. Moving on, now we're told the switch remains closed for a really long time. Okay, determine each of the following. The current in the inductor. So after a really long amount of time, then the inductor no longer has any voltage across it. Again, if we look at our graph, current versus time levels off asymptotically. So after a really long time, the slope of this graph, which is di dt, is equal to 0. And if voltage across an inductor is equal to L di dt, well, if di dt is 0, then the voltage is 0. So if there's no voltage across the inductor, then there's 0 voltage across the resistor. And with 0 voltage across the resistor, no current flows through the resistor. So what we have is current flowing through the battery, through the 10 ohm resistor, none of it through the 90 ohm resistor, all of it through the inductor, and the current now takes the outside loop. So that current is governed by Ohm's law. Current is voltage divided by resistance. We have a potential difference of 20 volts, but now there's only 10 ohms of resistance in the path, and so we get 2 amps of current flowing. All right, part D, what's the energy stored in the inductor? Or better phrase, what's the energy stored in the magnetic field of the inductor? Potential energy in an inductor is 1/2 Li squared. So here we get 1/2 times 2 amps. 1/2 times 0.5 henries multiplied by 2 amps quantity squared. Let's see. 2 squared gives us 4. 1/2 of 0.5 gives us 1/4. We just get 1 joule. Okay, moving on. At some later time t0, the switch is thrown back into the open position. For the very instant immediately after the switch is reopened, what's the potential difference across the 90 ohm resistor? So, this magnetic field that developed in the inductor and that energy of 1 joule that was stored in that magnetic field, well, the magnetic field can't instantly collapse to 0. That's because anytime there's a rate of change of magnetic field, there's going to be a rate of change of flux. And Faraday's law tells us that there's an induced voltage equal to negative N d phi dt. Or the induced voltage is equal to negative L di dt. Two ways of saying the same thing. If the switch suddenly thrown open, all of this becomes a dead branch, and the current that was equal to, what did we decide on, 2 amps in the steady state was flowing through the inductor. Well, for the for the inductor to maintain its energy or maintain its B field, it would have to maintain this 2 amps of current. And to do so, the only path where it can flow is through this right-hand loop and through the 90 ohm resistor. So the potential difference across the 90 ohm resistor is just equal to I times R. So it's 2 amps flowing through 90 ohms, and we get 180 volts. Interesting. Somehow we found a way to take a 20 volt battery and for a moment in time create a spike in voltage equal to 180 volts. You drop a switch, you wait for a long time until a steady state current of 2 amps develops in the inductor, and by suddenly throwing the switch back open, for a moment there's 180 volts across the 90 ohm resistor.